Good morning, everybody. It's March of 2020, and we are continuing our online learning modules for the COVID crisis. Today, we're going to be starting a new unit on waves, light, and sound. Now, if we were in a classroom, we'd do the wave round and round and round the classroom. So, if you've got some family members also hold up, get all your younger siblings together and do the wave. Track it around the circle. I suppose we could all do the wave on our Skype and Zoom screens like this. Ask yourself, what's moving around the circle? Is it the people? No, that's gym class. Is it your arms? No, that's the Addams family. Your arms are staying right where they are. They're attached to your shoulders. I'll grant it that sometimes they move up and sometimes they move down, but there's no net movement of your arms. They end up precisely where they are. Pause the video, talk for a few seconds, text with your friends, and press play when you've got the answer. What is moving around the circle? What's moving around the room? It's not the arms, it's the movement itself. Kinetic energy is moving around the circle, and that's your official definition of a wave. Wave is movement of energy without net movement of matter. Net movement means, yes, we know your arms move, but they don't go anywhere. If the particles all return to their original location, but the energy moves on, that's a wave. You are not the wave. You are the medium that the wave travels through. A wave, in sports or in a stadium, is transferred round the room by the medium of the people. The medium is whatever the wave moves through. We're going to classify 4 or 5 different kinds of waves. The first 3 kinds of waves are the physical waves we can see and touch and make ourselves. A transverse wave is an up and down wave. You call it a sine or a cosine wave in math class. This is the kind of waves where particles move perpendicular to the direction of travel. The wave moves forward as the particles move up and down. Examples of transverse waves include sine and cosine waves, certain components of ocean waves, S waves in earthquakes, and the kind of wave you do when you're flagging a taxi like this. Compressional waves are sometimes called longitudinal waves. This is where particles move parallel to the direction of travel. See high pressure, low pressure, high pressure, low pressure. The particles themselves move back and forth as the wave moves forward. Sound waves are compressional waves. They are pressure waves. So are P waves, pressure waves in earthquakes. So are shock waves and any other kind of wave that you make with pressure. Torsional waves are twisting waves. They twist back and forth. Unlike transverse waves, which move up and down, or pressure waves, compressional waves that move backward and forward, torsional waves move with the particles in circles going around the direction of travel. You see a lot of torsional waves in mechanical situations where something is twisting back and forth. You can make torsional waves yourself on a tire swing. These are the 3 kinds of mechanical waves. The other 2 kinds we'll talk about at the end of the lesson, and they are electromagnetic waves, which, by the way, just FYI, are also transverse. It's just you can't touch them. And gravitational waves, as explained by Einstein, again, also transverse, and so incredibly small that you are unlikely to notice them in your lifetime unless you're tracking the collision of 2 black holes. Let's classify what we see. What kind of wave is this? Pause, classify, play. That's right, it's a compressional wave. You can see the pressure moving back and forth. What about this? Pause, answer. Definitely a transverse wave. And this one, this is a torsional wave in action. Can you see the twisting back and forth? List other kinds of waves that you can classify as torsional, transverse, or longitudinal, aka compressional. What about these? That is a torsional wave in action. That is the Tacoma Narrows Bridge, and we'll talk about it the day we talk about resonance and aerostatic flutter. That bridge, as you can imagine, crashed and cracked itself to bits within a few minutes of this footage. What about this one? This is a queen wave. This is a torsional wave. Add it to your list. It's twisting back and forth. And this one? This is transverse. And this one? That is a compressional wave. Can you see the air pressure? You can see the cloud front as the water vapor in the air is pushed out of the way to make way for the smoke. Ocean waves are a special case. Ask yourself, why are these not true transverse waves? Pause, text a few friends with some answers, and then press play. Ask yourself, what would happen to the fish and the plants on the bottom of the ocean if these were true transverse waves? The whole ocean would be going up and down like this, bottom as well as top. Take a look at these yellow particles that are highlighted in the animation. They're not just moving up and down, they're moving forward and backward. These waves are the result of particles traveling in circles. Yes, they are partially transverse waves, but they also have compressional and torsional components depending on the axes that you use. These are classified very, very well in the special cases of seismic waves, earthquake waves. S waves in earthquake waves are surface waves. You can see it traveling through the surface now. And yes, you can see the bottom coming up and down. P waves through the Earth's crust are compressional waves. You can see the Earth being compressed and dilated as the wave comes through. Love waves are also two-dimensional hybrid waves. You can see the Earth shearing back and forward in 3D. These have S and P components. They're partially transverse, going back and forth, and partially compressional, as you can see what happens to that square of Earth over there. Love waves are very dangerous in earthquake waves because the ground shears right out from under you, and buildings do not like it when the ground with their foundation in it shears out from under them. Rayleigh waves are the kinds of waves we were trying to classify with ocean waves, where you can see there are transverse and compressional components. The top and bottom are moving up and down on the top of the medium, but the bottom of the medium stays where it is. Electromagnetic waves are a special case. Electromagnetic waves are their own medium. The medium is specifically the photon, but we'll get into that later. Electromagnetic waves are their own medium. They have an electric field vibrating in one direction, and they have a magnetic field vibrating orthogonally to it. List all the electromagnetic waves you can think of, and then classify them. The waves that you've listed can travel through space. That's what they all have in common. Some have colors, some are medical, some cook your food, but since they require no external medium to travel in, they can go where compressional waves, like sound waves, can go into outer space where there's no medium to compress. Here is the electromagnetic spectrum listed by wavelength. The longest electromagnetic waves are radio waves. You can't hear sound in space. Sound is a pressure wave. You can't pressurize the vacuum. What you can do is send radio signals. Radio signals are not sound waves. I'll say that again nice and slowly so you can write it down. Radio signals are not sound waves. You don't believe me? Listen. All around. What do you hear? If you hear nothing, that's right, and it's a great pity because you're being irradiated by about 40 radio stations right now. AM, FM, you name it. Turn on any kind of receiver with speakers and you'll hear, but you won't be hearing the radio waves, you'll be hearing the sound waves. That's what a speaker does. It converts electromagnetic signals, like radio waves, into sound waves that you can hear. If your speaker is on the fritz, you may be receiving radio signals, but you won't be hearing anything. Radio waves are used in communication for, yes, radio stations, also TV, cell phones, and all other communication. Microwaves are slightly smaller than radio waves. Instead of being measured with wavelength in meters and hundreds of meters, they're measured with wavelength in centimeters. You're familiar with the microwave that has a wavelength of 12.2 centimeters, which is the international standard for the common cooking microwave in a microwave oven. Infrared waves have their wavelength measured in fractions of a millimeter. If you wrote heat waves on your list of electromagnetic waves, think really hard. If you're standing under one of those heat lamps and the CTA waiting for your train, those are not heat waves as such, they're infrared. That's why the light is commonly colored red, so that you know it's a heat lamp and not just a lamp. Infrared rays are absorbed by living beings on Earth like us as heat, but they're not heat, they're infrared. Infrared is also used for night vision goggles in the police and the military. If by heat wave you meant it's really hot in August, that's not a wave, that's the weather, that's a temperature. Same way wind is not a wave. Wind, watch the leaves, it's moving particles from place to place. But if you're trying to transmit heat from the sun through us, it happens through infrared radiation. How do we know? It's got to be electromagnetic if it can go through space. Visible light is the next part of the electromagnetic spectrum. These are light waves. Some physicists are persnickety about calling them visible light waves because, well, they're all technically the same kind of wave. Really? They're all technically the same kind of wave? Sure. Just this has a shorter wavelength. Visible light runs from a wavelength of about 700 nanometers, which is a long wavelength, to medium-ish long. Let's talk about this in terms of frequency instead. Slightly medium-low frequency to low frequency, which is yellow, and medium frequency, which is green, and high frequency, notice the wavelength is getting shorter and shorter, to ultra-high frequency, that is to say the shortest wavelength our eyes can process, about 400 nanometers, all the way at the end of the spectrum. We're now down to hundreds of nanometers here. We're down to a very high frequency indeed, ultra-high. You're getting smacked and smacked and smacked and smacked with more of these photons every second, and that's why everything to the right on this electromagnetic spectrum includes in its properties being very dangerous. After your ultra-high frequency, we have ultraviolet. That's why we call it ultraviolet. Ultraviolet, higher frequency than violet. Infrared, lower frequency than red. Ultraviolet waves are too high frequency for your body to process safely. Look at the next lecture for when and why these can give you cancer. Shorter wavelength yet, we're talking fractions of nanometers. You're getting into X-rays, which are more toxic still, and getting into the pico and the femtometers, we have gamma rays, which are the most toxic of all. All these are electromagnetic waves. New to the list, experimentally confirmed as of 2012, are gravitational waves. Gravitational waves answer the question, how does gravity get from there to here? How can a force propagate across space? It can't be instantaneously. Nothing can travel faster than c, the speed of light. Not even information, not even news like, hey, somewhere toward the center of the galaxy, two black holes are colliding. Einstein predicted all the math for gravitational waves many, many decades ago, and turns out he was right. Check it out. Here's a model of the data we got from LIGO, which observed the collision of two black holes almost as soon as it was turned on. Spheres are symmetric. They send out regular gravity in all directions. But when they're in the process of crashing together and merging two spheres is not the same in any direction. The merge goes from a pancake to a banana, to a pancake to a banana, to a pancake to a banana as they crash, sending ripples in the gravitational field throughout space-time. Just how big are these gravitational waves? Well, from all the distance from here to Alpha Centauri, the nearest star, and back again, you'll notice a change in the length of a common meter stick, from shorter to longer as the wave passes through, of the diameter of one human hair. That's why we haven't noticed them until now. If you've got a Slinky at home, take it out, find some younger siblings, and shake it. Try to make transverse waves, compressional